as we start into bivariate data, we're going to look at a little bit of a review first. And our review here is going to talk a little bit about linear, nonlinear, which is it a function? We have some costs and figure out which is a better buy, or basically which is a cheaper per pack. And then we have some writing equations. And then what is the meaning of this? So here we go. Try this on your own and then check with me in class. All right, so we're going to do a quick explanation of what we have here so far. Number one, is it a function? Yes, because, or why is it a function? Yes, because it is a function because the y of x values only have one y value. So the x's don't repeat with a different y. And this one is not a straight line, so it is non-linear. Store A and store B over here. Store A, this is y equals 1.5x. So the cost is equal to $1.50. That's the cost per pack times the number of packs. So then on store B, we're going to have to go from the table and make an equation. So on this, we went and found that the change of y each time and the change of x each time. The change of y is 4, and the change of x is 2 each time. So we have 4 over 2, which is just 2. So my slope is 2. Now my y-intercept, just because we're going to go ahead and make sure that we know the value, we're going to go back 4 each time. That would give me a 4, back 4 more, and that gets me to 0. Same thing up here. Back 2 gets me to 2, back 2 gets me to 0. I want to know the y value when x is 0, so the y-intercept is 0. So my equation is y equals 2x. So if this is $1.50 per pack, this is $2 per pack. So store B charges $2 per pack. It is the one that charges more. How much would it cost for 8 packs of gum at store A? Well, store A is the $1.50 per pack. So $1.50 times 8 gives me 12. So $12 for 8 packs of gum. So now we're looking at 3 and 4 and 5. So write a linear equation that represented by the graph and the table. So here's the graph, and then this one's the table. So the graph, basically on each of these, I'm looking for the slope and the y-intercept. So I always start with the y-intercept because that's my starting point. My starting point is down here at -4. So y-intercept is -4. And the slope, I'm looking for a nice crisscross on the grid, and I see one right here is a nice crisscross. And then right here would be a nice crisscross. So it's going to be down 1, 2, 3, 4, down 4, over 1, 2, 3. So my equation is going to be y equals -4 over 3x minus 4. On number 4, I'm working from a table, just like we did up above with the gum. So I know the change of y and the change of x. So my change of y each time is going up by 0.3. And over here on the x's, I'm going up by 1 each time. So my slope is the change of y over the change of x. So it's going to give me 0.3 over 1, which is just 0.3. Oops. So, oops, I don't know why I did that. So y equals 0.3x, that's my slope. And then I need to find the y-intercept. The y-intercept is the value of y when x equals 0. So I need like a zero-sum number. So here's my zero-sum number. It's going to be 1. So plus 1. Number 5, does the function y equal 3/4 plus 1x represent a linear function? Many people in class were saying no, but it is in fact yes. It is linear. If I just rearrange these two numbers, we would be saying y equals 1x plus 0.75 if I gave it a decimal. And that is linear. It would make a straight line. You can always check it by plugging in input and output and see plotting some dots. But it is linear. It has a degree of 1, meaning no exponents. The next problem that we have on this warm-up is we have the giant panda. He lives at the Washington, D.C. Zoo. And what does this point on the graph tell us about this panda? Well, here's the point, 3682. We really have to look at our axes, the labels that are on those axes. So on the x-axis, because this is your x value and then your y value, on the x, it's age in months. So age in months. And the y value here is the weight in kilograms. Weight in kilograms. So if I know at age, when, and how much, so when he's 36 months, so at 36 months, the panda weighs 82 kilograms. Then we're going to do the graphing practice. This is checkpoint 2. The notes are checkpoint 1. This is checkpoint 2. So go in checkpoint 2, follow the link. Then we get to check, this next piece is really getting into the scatter plots. Scatter plots are going to be a useful summary of a set of bivariant data, meaning two variables, x and y, that's drawn before working out the linear correlation. So the linear correlation coefficient right here, that is your slope. And we're looking for a line of best fit. So a line of best fit is going to be like a y equals mx plus b. It gives us a good picture, visual picture of the relationship between two variables and helps us in an interpretation so we can tell what's happening of the correlation. So it's going to show trends. So as we look at this, the first part we're going to look at is going to be this pattern that as the independent gets larger, the dependent also gets larger. So as x increases, y increases. This is positive. All right, so this is a positive correlation. Basically, something like the more hours I work, the more money I make. Basically, as one goes up, the other goes up. And you can come up with a whole bunch of them that we did in class. The next one is as my independent gets bigger, so as x gets bigger, it increases, y decreases. This is a negative slope. For instance, the more I spend, the less money in my account. And the next one over here is kind of like a hodgepodge. It's all over the place. There's no correlation on this one. So, oops, no correlation. It's all over the place. So something that would have no correlation would be like the size of my foot, oops, to the level of my IQ. All right. And there are a whole bunch of things like eye color and how old you are. Yeah. Okay, so concept 1, we're actually going to get into now plotting some dots. So concept 1, so let me get rid of this too. Delete. All right. This one is a real world problem. It is the year and then the number of tornadoes. That is tornadoes, by the way. So this is my x-axis. This is my y-axis. We're going to call the input is your x, and that's going to be the year. And the output is going to be the y, and that's going to be the number of tornadoes. One thing I do want to make sure that we start looking at, always, 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 check your graph scale. So as I look at my graph scale here, and I see that, hang on. So as I'm looking at the scale on this one, this is of course by 10-year increments, but the y-axis here is actually talking about the number of tornadoes. This one is 600. So if I looked at the breaking it down from 0 to 600 divided by 1, 2, 3, that's going to end up being in 200s. So I'm going to break it down into 200s. So this would be 200, 400, 600, 800, 1,000. So now when I plot my dots, again, it's just going to be an approximate. But at 1950, we're looking at 201. 1955, which is halfway between, we're looking at 593, which is about right in there, maybe close to 600. At 1960, we're looking at 600, a little over 600. 1965, we're looking at almost 900, which would be kind of halfway in between here. 1970, we're looking at 650, so here's 600, a little bit more than that. 1970, so like right in there. 75, we're looking at 19, 99, 19, which would be about a little bit more than that maybe. And 75, so then 80 is 866, so there's 9, so a little bit below that. And we're just kind of estimating, okay? It is an estimate. Now, if I wanted to put a best fit line in there, basically what I would do is I would take a line and kind of draw it in the middle of it all. I did touch one dot, but that does not matter. My line could be anywhere from, it could be down, it could be up. Basically, just trying to find an average line right through the middle of it all. Then the next part right here, we have the panda. We're going to be plotting dots. So checkpoint, maybe. This is going to be checkpoint 3 and 4. Go ahead and make sure that you snip and clip those and put those in when you request for feedback. Those are also in Summit. Concept 2, which equation best models the data in the scatter plot? So what I would like you to do is I would like you to take each of these and graph them and see which one fits best. So try example 2 and 3 on your own and then come back to me. All right, so I'm going to start in with the first one. I'm going to switch colors each time. So A, I'm going to do in purple. First thing I'm going to do is check your scale. My scale on here is 2, 4, 6, so this is going to be a 4. So my 1 is actually here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, and then on the x-axis, it's 1, 2, 3, 4, 5, 6. So these are one by one. Let's actually switch this to blue since I used purple. All right, so I'm going to go up 4. Put a dot, so there's 2, there's 4, put a dot, and I'm going to go down 1, so it's down 1 tick mark over 1, down 1 over 1, down 1 over 1, I'm hitting dots right and left, down 1 over 1, so looking from here to here. So my first line is going to be somewhere like this. And I'm going to change that color to be a blue one. Then the next one we're going to try is let's do a pink one maybe. Let's do B, pink. So we're going to go up 5. There's 4, here's 5. And we're going to go a slope of 1, which means up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And draw another straight line. And let's change that one color to being a pink. Now, I would say blue is better than the pink at this point. I would say pink is probably a no. Blue is a maybe. That's pretty close. C. Let's do C as being red. Oops, maybe. So we're going to go up 2, put a dot, and my slope is -5. So 1, 2, 3, 4, 5 over 1. And I think 2 points here is enough to get some gist going on. It looks like that. That doesn't even look like it goes hardly through my data. So let's go ahead and make this one a red one. And then the last one, I'm going to say no to that one as well. And the last one I have is -2. Let's go with green. Down 2, put a dot, and then up 3. 1, 2, 3 over 1. Up 1, 2, 3 over 1. And this one's a positive slope, but originally it looks like it was a negative slope. So I'm thinking that this is a definite no. And instead of having to graph all of them, if you can go with a slope in general, you probably don't have to graph them all. Because I could have told you, based on my slopes, that this graph itself looks like it's a negative slope. So anything with a positive slope, I could have just marked off right away. And then I would have worked with my 2 negative slopes, which happened in my blue and my red. So blue is definitely the best choice. The next one, let's kind of think about that same thought process. This is a positive slope because it's commonly going up. Okay, so its correlation is positive. So I can immediately get rid of this one because that's a negative slope. Now, I don't even have a negative y-intercept on here. So I could actually get rid of this one as well because this is -3. That'd be way down here. It's 1, 2, that'd be like down here as a starting point. That's not anywhere near my data. So I could probably get rid of that one as well. Now, between my 2 pieces of data, they're relatively close. Check your scale. I've got 1, 2, 3, 4, 5. They're a 1-to-1 correlation. 1, 2, 3, 4, 5. 1-to-1. So I'm going to go ahead and do blue. Let's do green here with B. I'm going to go up 3. 1, 2, 3. Put a dot. And up 1 over 1. Up 1 over 1. Up 1 over 1. I'm going to go down, back, down, back, down, back. And draw a pretty line. Roughly through there. Then I'm going to do a pink one, and I'm going to do the same thing with this one. I'm going to go up 2, put a dot, and I'm going to go up 1 over 2, up 1 over 2, down 1, back 2, down 1, back 2. And it is, I mean, it touches some of the data, but in general, I don't know that this depicts the average of our data. So I'm going to say green is a definite, and this pink one is a no. So I'm going to say green is the best one that we have to choose from. Now down here, I was a little bit forward, and I put in some lines for you. So let's figure out which line is which. But first of all, let's look at our scale. And as we look at our scale, we're over here, it cuts the scale, and we start at 40. This would be 45, 50, 55, 60, 65, 70, 75, 80. So they're really going by 5s. And down below, they're also going by 5s. So if I'm going by 5, that means over 1 is actually over 5. So since I have this, I'm looking at my slopes. I would change my slopes to being a little bit bigger scaled. So -2/5, I'm going to make that -20 over 50. It'll kind of spread out my data a little bit better. So the first one, A, I'm going to go up 80. And if I look at this, that's going to be in blue. I'm going to go up 80, put a dot. And then I'm going to go down 20 over 50. So if I go down 20, so there's 10, 20, and over 50 gets me to like right here. Oops, right here. And that happens to be on the blue line. So the next one is my pink one, I think. I'm not sure. Here's pink. If I start at 75 and I go down 10, 20, and I go over 50, that gives me right about there. So yeah, that is pink. It's kind of through my data. Pink is pretty much right through it. And then C, this is going to actually be the black one. C, I did a straight constant 60. I'm going to say that's a no. But all of these have negative on the slope, so I really have to graph each of them. And the last one, I believe, is my green one. I'm going to go up 75, and from there, I'm going to go down. In this case, I would go down 30 over 50. So down 30, so there's 10, 20, 30 over 50. And I feel like that's a little bit low on my data. So I would say the best fit is going to be that pink one right in the middle. So I would say B. And why? Because it goes through most of the data, like cuts through most of the data. Not necessarily touching the data, but it goes right through the middle of it all. It's an average line. Okay, then we have concept 3. I'm going to pause and we'll do concept 3 on a separate video.